So hello everyone, welcome back to the another lecture. So my name is Ashish and today is the fifth concept we are going to learn in this playlist of the dual active bridge converter. Okay, so far so now we have basically pretty much clear about the DAP converter, single phase shift modulation, how exactly it will happen and how to calculate the different thing in a single phase shift. All these things we have learned. Now it is time to implement the same concept in the MATLAB, okay, so that you can understand how exactly we can implement it. So in this particular video we will talk about the open loop MATLAB simulation of DAP converter using the single phase shift. Okay, so this video is about the open loop, and the next video which I am going to make, that is about the closed loop strategy, how exactly we can implement the and why there is a requirement to go for closed loop. Those all concepts we are going to discuss. So in this video I will show you the MATLAB script first, that how I have developed my MATLAB script for the single phase shift modulation. Then open loop simulation we will do, and then after that what if the phase shift angle is 0. Okay, so if I will make the phase shift angle between these two bridges equals to 0, then whether the power is transferred or not. This question I have asked you at the maybe lecture number 2 or lecture number 3. Now again the same question I have keep it here, and again you need to answer this question just by I will just show you the result, then you decide what exactly has happened. Okay, and then in maybe next class I will explain you what is the exact phenomena happen when we keep the phase shift angle is 0. Okay, so let's get started with the MATLAB simulation. So here we are in a different window. Now I have make one script for you. Okay, you can just see the entire script, what exactly I have written down and all, and how I have developed the entire script. Okay, so when you do any kind of simulation, make a habit to make a really good script. Okay, so next time when you basically do for some different value, you don't have to compute manually all the things. Only one script if you have, just change the value, you will get entire thing automatically. Okay, so that kind of habit you have to make a really good script. Okay, now DAP converter parameter in SPS. Okay, so simulation parameter. So whatever theory we have learned, that theory I have tried to keep it here initially. Okay, so that whenever I will open the script in future, if I forgot something, so I can just read it out these things and I can understand, okay, these are the things I need to do when I will go for single phase shift. Okay, now how I have developed my entire script. So these are the few command: clear, close all, CLC, that you know. Now the input, I will not go in much more detail, I will just show you that what I have tried to do in this. Okay, now this parameter we have initially taken that my V1 is the input side DC voltage 800 volt, V2 is my output side DC voltage 800 volt, my power output requirement is 30 kilowatt in this case, switching frequency is 100 kilohertz, and N, that is the N1 by N2 I have considered here as a 1, because why, what I have told you that V1, how to decide the value of the N1 by N2, just see the value of the V1 and V2. Okay, so now they are closely equal, V1 and V2, so I have just keep it as 1. Okay, if it is 800, if it is a 1200, I can go for maybe N equal to 2. So that is all up to the you, what value of the N you will choose. Okay, so that is the initial point to start with. So these are the some user input, you can say. Now L value I need to calculate. Now how I can going to these are the few things for plotting and all, those are not required as of now. Now my TS, that is a switching period is 1 upon Fs, and I need the omega, that is the 2 pi Fs. So that thing I have just calculate. Now I need to calculate the value of the L. So I told you that initially we need to have some guess value, right? So I have calculated the L required value. What is this L require? This L require, this is the formula for actually maximum power, right? So I told you that I am considering here the P out as a maximum, and my P out is 30 kilowatt, which is not the maximum power, because maximum power occur at D equal to 0.5. So I have to keep some margin, right? So initially by keeping P out as a maximum power, I have calculated the value of the L required. So this is the formula I have tried to calculate. So I get some L required. After that I will calculate the value of the L. So I told you that some safety margin I am considering. So initially maybe at the top I have considered some safety margin of 0.8, which we also discussed in the previous class. So I have computed the another L with the multiplication of the safety margin. So with this help of the L, I will calculate the P max again. So again, same L I have keep it here, and I have calculated the P max. What exactly P max will come? It will definitely come greater than 30 kilowatt. Okay, and this is the value, and we know that particular curve, right? So at del equal to 0.5, when it is del equal to 0.5, del equal to 0.5 corresponding to 90°, right? So at 90°, I should get this particular value of the P max, right? This is what we wanted to say, but I don't want it to operate at del equal to 90°, and that is why I will shift, I will keep the limit I will keep some provision for my maximum power. So my maximum power will come something else, and I will keep this limit in such a way that my actual power output will come less than 90°. Okay, so this is the basic motto of doing this. Once that Pmax and all done, then what I told you, that we need to calculate the phase shift angle. We have calculated the L, then we need to calculate the phase shift angle. So few more things just written down for understanding purpose, just for printing purpose. And basically just I am checking here that whether my L is greater than L max. If that is the case, then I need to change something, right? So those things only I have tried to calculate. Now once that is done, then I will go for calculation of the phase angle, right? So I decided, I told you that we have keep some value of the K, which is also we have learned in the previous class what is my K, and that mistake also I have commented out, right, that I have missed this particular term. Now here n is n1 by n2, that is why it is in the denominator. Okay, otherwise if I will use the small n, that should be in the numerator. Okay, so those things, just try to see how I have developed the script, so that when you developed it by your own, you are very much confident that okay, this is how I can created the entire script for single phase shift modulation. Okay, then I have calculated the K value. Now I need to find out the roots. So how I can find out the roots? Just basically using the MATLAB script only, I can easily get the roots. So I calculate the disk, that is you should know that b square minus 4ac, right? That particular term I have calculated, and I have tried to calculate the roots of my particular equation. So I get phi in radian, phi b in radian, so two roots I will get. So very easy things to do. It is very easy concept. Okay, you know how to calculate the roots. Just I have written down in the form of the code. So once that is done, I am just checking that which particular root is my basically come under the particular value, and I was just checking that whether with this particular phi value which is calculated, whether I am getting the p actual calculated with is within the limit or not. So it should match actually, right? Because we have calculated the L value, we have calculated the value of the basically del angle del. So I should get theoretically exactly the same power which is required, right? So all these things I am just checking here, and basically again maybe this is in the radian. I have maybe calculated the same thing in the degree as well, somewhere or somewhere I have maybe calculated. Okay, and just printing the few things. Then I am calculating what is my input current value, what is my output current value, what is my load resistance, v square by p out, because we are doing this with the resistive load. Okay, power, my power 30 kilowatt, how I will get with some resistive load I am keeping. So that is why this thing I am just calculated for my reference. Okay, and just for the sake I have just plotted my p versus phi, so just to see where exactly my point is coming on the that particular plot. That particular plot of the half sinusoid, right? So just to see where that particular point will come of the maximum power, just I have written down some code for that. Okay, and just saving the result for my reference, and that's it. Nothing is there. And one more important thing about the C calculation. Okay, so considering some 3% ripple so of the V2, because V2 is on the output side, so 3% of the V2 I am considering, and then I have calculated the C value. Okay, so C value calculation we have also learned. So this is the approximate value. So I will, whatever value of the C comes here, I will consider 2 to 3 times. Okay, when do the simulation. And another part is, okay, so TS, so this concept also I told you that TS correspond to 360°, then TS by 2 correspond to 180°. So selected phi, if it is coming 40° or something, then what is the actual time? So for that, that selected phi time, so basically equals to, I write it down, TS by 360 into, so that 360 divided by TS is equal to basically we have some value of the phi divided by some x. So just cross multiplying and calculating the what is the actual time, and I am just calculating it some ratio. Why I am calculating this ratio? because this ratio is the something number which is multiplied with my TS will give the total basically phase shifting. Okay, so just for that purpose we have calculated, but we from this particular point we understood that okay, this much of phase shift, this much of time of phase shift I need to provide it between the two pulses. Okay, so just for that we have just calculated the few things. Okay, so I will just run the script once and then I will show you what are the different parameter I am getting here and all, so that once I hope so you understood this particular script. In future you can just maybe see this particular script once just by pausing the video and try to write it down by your own, so that you have maybe you are not that much familiar with writing the script, so that is also one of the exposure you will get. Okay, so I will just running this particular thing once. So now you can see that the whatever code I have written down based on that. Okay, so this is the point where 90 degree will come, so maximum power it is coming as 37.5 kilowatt. Okay, so for the L which is we actually calculated L require, if I will use that particular L at del equal to 90 degree, I can have the capability to transfer the power of 37.5 kilowatt, but my requirement is 30 kilowatt power transfer, so that will come at this particular point, that is 49.75 degree. So I have to choose this particular point, and this 49.75 degree correspond to what particular time. So for that we have calculated the this particular things. Okay, so this is the graph. I hope so you understood what is this graph, and this is the selected phi time, so I need to provide the phase shift of 1.38 microsecond. Okay, so this is the thing we understood. Then another few thing which are we have calculated, so we know that v1 v2 this is the L value which is coming. Okay, so L require is 2.66, so we have considered the safety factor of safety margin of 0.8, so 0.8 multiplied by this, it is a this value. So I am going to use this particular value to for my simulation and that phi angle, then only I should get 30 kilowatt of the output power. So these are really stringent. Okay, I am doing in open loop, so I have to keep the value of the L as well as the delta angle, that particular time should be match exactly, then only the properly how much power I need to transfer that will come, otherwise it will not come. Okay, and other thing load resistance value, everything we have calculated here. Okay, so all parameters are there. Now we will jump to the Simulink model, how we are constructing the Simulink model, and what is the how we can do the open loop simulation, that part we will see. So here we are in the new window. Now you can see that how I have constructed the open loop model. Okay, just very briefly we will see. So this is my DC voltage source. So what value I have keep it there, that is a V1 value which is 800. Then basically I need the 4 MOSFET. So you know that you are watching this advanced power electronic converter, DAP converter. So I hope so you know about the MATLAB interfaces and everything. Okay, so only thing how to implement, that is the case. Okay, so just write it down the MOSFET, you will get the MOSFET here. Then just do the connection. So I have marked this as 4 getting signals I needed to basically provide it to this, like S1, S2, S3, S4. Then basically one transformer is required, which is a linear transformer. You know linear transformer, right? So once you take the linear transformer, just open this particular transformer and just assign the values, like what is my nominal power and frequency, that is 30 kilowatt. 30 kilowatt is my power. It is in VA, but I can keep it 30 VA. Okay, then 100 kilohertz is my basically frequency. Then input winding parameter, secondary winding parameter. So these are we have written down, and third winding I don't need, so I have ignore it. And magnetizing resistance inductance, this value should be really high. You know, this ideally this should be infinite, because I am not using the LM here. Okay, so LM don't have any role to play here. It is not the flyback converter, right? So that is why it's very high value. So this is how we can put the parameters for my linear transformer. Then this L value, so you can see that what is the L value, the same value which we have calculated, I have tried to keep it here. Okay, then once that is done, then on the secondary side again 4 MOSFET I have arranged, and the getting signal for them is S5, S6, S7, S8, and then my one capacitor is there, which is a load. Now this value I will keep it as just C. So it's a 1 point something is coming, which is a 15. So I told you that just multiplied with the 2. Okay, 2 times or 3 times you need to keep, that's more than enough. Okay, so it is just 30 or something micro farad coming. So I will just apply it, and my load resistance you can see here. What is the load resistance? So load resistance is R load, which is calculated from the script. Okay, so once that is done, what other scope I have connected here? So I wanted to see what is the input current which is going to be flow here, then what is the voltage which will come across this particular terminal. I marked it as a VAB, and what is the voltage come across this terminal? I marked this as a voltage V A2B2, and what is the current which is going to be flow through this particular inductor. And based on how the current is there, that will decide which modulation technique we are interested in. Okay, so now we know that for a single phase shift modulation, what is the nature of the current that which will be flow across this particular branch. Okay, and what are the other parameter I'm interested in? I wanted to see what is my output voltage and what is its overall average and output voltage. It should come 800. And what is the output current. Okay, so all those parameter I need to see. Now you know that basically it will operate at the 50% duty ratio. So where these two switches will on simultaneously and these two switches will on simultaneously. Okay, this very basic fundamental thing we are already seeing. Okay, what is the pattern of the gate pulses we apply in the single phase shift. So the same thing I try to implement. So now this is the pulse generator block. You know that we are doing in open loop, so I am using the pulse generator block. So pulse generator block, amplitude is 1, time period is 100 kilohertz, and I will creating the one pulse of 50% duty. Okay, so this is a 50% duty. Now this 50% duty will go to two blocks, right? This S1 and S4, because they will operate in the they will turn on at the same time, right? You know that particular thing. So I am giving the S1 and S4 the same pulses which are generated here. Now S1, S2 and S3 should get the complementary pulses, right? Because when S1 and S4 is on, that time S2 and S3 should be off, and when S2 and S3 is off, S1 and S4 is on. So this is this thing we know. Okay, so whatever pulse I have generated, I am just keeping it as a NOT gate. What NOT gate will do, it will complement the pulses. So when it is on, that time it will make it as off. Okay, so just very basic 4 pulses I have generated on the primary side. Now come to the secondary side. What is my requirement? Whatever pulses are getting to S1, that should be phase displacement, that should be displayed by some angle, right? And that angle, that time we have calculated, right? So now there is a block to displace that. So same pulse I am taking and giving to one particular block. That name of that block is a variable time delay. So there is a block called as a variable time delay. So you can just open this particular block. So inside that I don't have to, I guess nothing we need to provide, so I can just see quickly. So inside this I am not providing anything. So what input it require, what is my the first input, this block will take it as what is my pulse I need to apply. So this is the first thing. Then second thing is T0 input. What this T0 input is, whatever signal is receiving, I need to phase displace it by what particular time. So that is the thing we are going to generate here. So this number 0.1382 we have calculated, this corresponding to time. Okay, even I can directly give that particular time here, or what I am doing there, TS multiplied with this particular time. So this is overall the same time will come. So once that signal I am giving here, it will generate the phase shifted signal, which I am going to provide to my secondary bridge, that is S5. So you know that the operation of this S5 and S8 will turn on at the same time, and S7 and S6 will turn on at the same time. So the same thing I am doing here. So S5 and basically S8 are my two signals. So S5, S8 are the same, and basically complementary of the S5 is my S6 and S7. So just only thing is we need to implement this particular block. Okay. So once that is done, we are created the all the gating signals. Okay, on the primary side logic is very simple, on the secondary side again logic is very simple. Just I need to basically displace the my secondary bridge input signals. Okay, so the same signal I have taken and I have just phase shifted it by what is required time I need to have. Okay, now I will just run the simulation and then we will see the results. So I will quickly run the simulation and then we will see all the results which are coming. Okay, so just wait a minute, it will compile and then the simulation will get ready for us. Okay, so it is taking bit of time, so just wait a minute. So okay, it is started running. So we can see the output initially, whether I'm getting the output correctly or not. So you can see that what is my required output is 800 volt. So within very quick time I reached to 795, and it is stable, I guess, at the 795 or 796 I can call. Why not it is 800? Because these switches which I have considered, they are not ideal, first thing. Okay, so because of that some losses will be there, and it is coming roughly around 796. Okay, and which is fine because we are operating in the open loop. Now we can see the waveforms which are coming here. Just I will show you once what is the output voltage and output current, whether the multiplication of these two leads to 800 volt or not. That particular thing we will see. So just I will quickly show you. So you can see that roughly 800 volt clear output I am getting here. Okay, and my current is what? Current I will just show you. So current is coming up around I guess 37.5. So okay, so some 37.5 ampere of the current is coming. So if you multiply 37.5 with the 800, roughly we'll get the 300 kilowatt, 30 kilowatt as the my required power output. So you can see we have done in the open loop, but we are getting really good output. Okay, now we will try to see the few more waveforms. Okay, so this is about the output. Now how my this particular waveforms are coming, that we will try to see. That is my primary side bridge VAB and secondary side VCD. Okay, so just those waveform also we'll going to see, and what is my current nature. Okay, IL we know how exactly it will come when we operate our circuit in the single phase shift. So quickly I will show you, just zooming at some particular portion. So now you can see exactly how it is happening. So this is how we will get, right? Increase, then some decreasing or increasing slope, then decrease, some again decrease or increasing slope. So this is how we have also seen, and the same kind of waveform we are also getting. Okay, so this is what we are expecting. Now with what is my VAB or VA2B2, just see once whether they are displaced or not. So they are also displaced kind of thing. Okay, the displacement is between the whatever angle we have provided, the same displacement we can also see here as well, right? So this concept we already know. Okay, and we are getting the output exactly what we require. Now we will see the gate pattern once, whether the gate pattern is also okay or not. Our simulation is running fine, so that means our gate pattern is also will be perfectly fine. So few of the gate signal which are required, I have just tried to keep it here. So just I will show you once. Just I will zoom it for you. So you can see that. Okay, so this is the time where the phase displacement is happened between the S5 and S6, and S1 S2 are complementary to each other, and S5 and S6 are complementary to each other. Okay, so you can see that clearly there is a phase shift is happened. Okay, so all the waveform we have seen. So now one more waveform I will just show you what is the exact nature here. That is also the one thing we need to see. So this particular waveform, this is also we are familiar, because based on this waveform only we have derived our so many parameters, right? What is my I naught and all, and what is the nature of this, this is also we have already know. So this is what it is, and exactly this is what we have also derived. Okay, and based on this waveform only we have come up with some different relations, right? So all the waveform whatever are available we have understood, right? Now what is the next thing we need to understand is, okay, we are doing in the open loop. Why we don't go for open loop? If I will just change a little bit of this number, my power output will completely change. So let us say I make this as 0.5. so now I will run the simulation for you, and you can see that my output power will be completely different right now, because a phase shift angle is changed. Another parameter I will change after some time. So you can see that what is the exact output I am getting, it will taking. So it is 910. So you can see that it is really completely my system is collapsed. Only just by changing my phase shifting angle, the system is completely collapsed. So this is not what is my expectation, right? Also, what is the second thing, I will keep it as it is. So if I will change my value of the L, that will also affect the system to very great extent. So let us say I multiplied with the 2. Okay, so it is now 2L. Now if I will run the simulation and if I will show you again, really completely different kind of output you are getting. Just see once whether I am getting some output or not. It is taking a bit of time. uh, okay, so some 400 volt or something is coming. So when I will make L to 2L, my output is completely directly become half, right? From 800 volt to it will directly come to 400 volt. So this is how the system is very sensitive. When I will change one parameter, it will highly reflect, it will highly disturb the second parameter. So because of these issues, we will not go always for open loop simulation, okay? Because secondary side is something which we need to control, and when we go for the closed loop control in the next class, we will keep this as open loop, which is perfectly fine, because we know that this sequence is already known. But how and what particular phase shift is need to be provided, that should be calculated based on the my output voltage or my output voltage as well as my what is the current flowing through it. Based on that, we can go for the further calculation, okay? So this is how we develop the things. I hope so you understood most of the thing from this particular video. Try to analyze the thing as much as possible, then only you can come up with really good things, okay? Now one case study which I have discussed with you, like what if I will not provide the any phase shift. So let us say this phase shift is 0 and my there is no phase shift between the two bridges. Now I will try to run the simulation. Let us see whether I am getting some output or not, and whether if I am getting some output, what is the reason for that. Okay, so all these questions are there that should come in your mind, and try to answer yourself first. Somebody has commented, I guess he tried to attempt the answer, and that is perfectly fine. So now some 90 volt or something is coming here. Why this thing is happen? Can you guess? I am not providing any phase shift, still I am getting some output. Let us see what is my overall maybe power output. So power output is drastically reduced, so it is, I guess, almost 100, and this is almost 5 or some so it is 100 into the 5. So just 500 watt of power is transfer, right? But that I am not interested in this particular thing, right? Another thing, few waveform we will try to see. So some power is transferred, okay, with even if I will keep the phase shift angle as 0, some power is transferring. Now I am interested in here what is my VL waveform, okay? So let us try to see my IL waveform as well as VL. VL is nothing but the VA1 B1 minus VA2 B2, right? So it is completely square wave. There is no some sort of duration which is coming which is flat, okay? And you can see that VA1 B1 is okay, but VA2 B2 is taking bit of time to basically it is not directly constant. It is coming from some maybe 70-80 volt to 100 volt. So why all these things are coming? So I want you to answer this question first. I will discuss this again in some other video, okay? Because it will take some time to understand that even without the phase shift, how exactly I'm getting some power, and how this particular L will now play and come into the picture and everything, okay? But you attempt this question first, and then in after few videos I will come up with the answer to this particular question, okay? So with this I will conclude this video. I hope so you understood how we can develop the open loop model, and now why there is a requirement of the closed loop to go for, okay? And in the next class we will see how we can implement the closed loop simulation of the single phase shift, okay? So with this I will conclude this lecture. Thanks for watching this video. See you in the next class.